polar covalent, or polar versus nonpolar, and so forth. So tell me, so you're looking for the greatest intermolecular force or the greatest interparticle attraction. And with that, you know every single one of these have many secondary IMFs or secondary attractions, but they're not the primary ones. So we're looking for the most significant. So between the two, what first of all, identify what these first two are. What kind of attractions are happening? Okay, ionic and which one? Say again? Dipole, because it's a polar molecule, dipole attracts. Which is stronger? Ionic, because we have a large lattice energy associated with this one. This would be the higher interparticle or intermolecular force. We say interparticles, we're not like discriminating against those ionics versus covalent. Next one, what kind of particles are these? Give me some stuff, man. They're what? Okay, but why? Because they are polar molecules. Okay, so you use your terms there, polar molecules. You guys should be completing this with me, okay? Polar molecule, this one's a dipole force. This is polar molecule dipole force. So you maybe drew this in your head or on paper. What structure, like what does this look like? Yeah, but what are they? Trigonal pyramidal, right? Lone pair on top of phosphorus. Fluorine and chlorine both have lone pairs. Well, which has the higher dipole force? You say that. You have a reason for that. That has nothing to do necessarily. Okay, so I know that does have something to do with the polarity. It has maybe slightly higher partial negative, partial positive, but that's not the criteria we look for dipole forces. Why? Higher molar mass. If you're more massive, then you tend to collect together with partners, your other neighbors. This is on your video from last night. Molar mass is the criterion you look for in terms of the dipole forces as a comparison point. The higher molar mass means the higher dipole force, so we say that's got the stronger force. Okay, so I'm just going to put MM here to remember molar mass. Next one, what are you seeing here? Comparing what? Two ionics, right? So what's the criteria you look for if you're comparing two ionics? We talked about this one last unit, actually. So it deals with Coulombic attraction, where the two parts, charged product. So you're looking at the charged product. Okay, well then you look there and you're like, okay, 2 plus 2, 2 minus, 2 plus 2 minus. So charged product is not going to help us. But that is the more significant portion of Coulombic attraction. Remember, its force is equal to charge times charge over distance. So now we're considering distance. Which ones are closer? Why?
Because it's smaller.
Right, so atomic radius, calcium's here, barium's 2 below it. So calcium is smaller than barium. If you're smaller, you get closer to your anion, so the bond is stronger. The
Molar
force
mass doesn't work for ion.
no, molar mass does not work at all because we have the two other criteria. We look at charge product, if that is more. You have the same charge product, you look at distance because according to Coulombic attraction, the force of attraction increases when the distance decreases. Okay, they're inversely related. So calcium oxide will be stronger because it's a smaller cation, higher lattice energy. You can keep going, right? Okay, next one, what are we looking at? Okay, but why radon? We're looking at atoms, right? We're looking at elements.
Will this fall into the crystalline?
This is actually more gaseous. It could be a crystalline atomic solid. It could be, and it might be. But right now, you notice that you are just simply comparing the atoms. So the force of attraction, if anything, is probably London dispersion, right?
Yeah.
Because there's no polarity. It's going to be a nonpolar atom. So what would you be considering? So the electrons, right? The London dispersion here is the electrons, which would be the molar mass doesn't go along with it because it does condense bigger, more likely to condense. Anyway, who is it? Radon. As you can see, it's bigger. It's about 3 down from argon, and it's got more electrons. Water versus hydrogen peroxide. Do we have any reasons for our statements?
Hydrogen.
So is hydrogen peroxide. Okay, we got a 50-50 people, but we need some reasons.
Hydrogen peroxide.
What hydrogen peroxide? Hell, let's draw hydrogen peroxide. So water, we know water looks like. Oh, tell me what hydrogen peroxide looks like. What do you guys think?
Two H's bonding to another oxygen, or both bonding to a hydrogen.
OOH page, right? Lone pair, lone pair, lone pair, lone pair, whatever, right? So basically, water's got two places for hydrogen bonding. The H's can attract to two other water molecules, or really it's the lone pair that's creating that partial negative that's going to be attracted. This has two places for hydrogen bonding, and this has two places for hydrogen bonding, right? So if you have to compare them, what do you compare? You've been saying this all day. Molar mass. Thank you. Hydrogen bonding, hydrogen bonding. They're both polar, so they're both polar. They're both hydrogen bonding. They both have two places for hydrogen bonding. Technically, hydrogen peroxide has more because even though it's got that branch, and I drew it that way, these and these lone pairs can technically hydrogen bond more than these. And if you just need to resort to a kind of general criteria that we continue to resort to, it's molar mass. This one's got one more hydrogen, or actually almost double in mass. So hydrogen peroxide would be the stronger due to more locations for hydrogen bonding and the higher molar mass.
But why? Like if I think about it, hydrogen peroxide evaporates. Like it's always.
Hydrogen peroxide is actually, nobody has pure hydrogen peroxide. Hydrogen peroxide from Grishter is 3% hydrogen peroxide. It's mostly water.
Yeah, because it evaporates.
But it's mostly water, and it can evaporate itself, but it's actually the lack of it. It can interact with water, but doesn't interact with water as well as some other things. We're actually going to get into that with solutions in about a week. But it doesn't evaporate as much as water does. Water actually evaporates pretty quickly too. Not as quick as like other things. Don't get me wrong. Okay, hydrosulfuric acid or dihydrogen sulfide or H2O. Why? So you're comparing that to what? Right, this is polar, it undergoes dipole-dipole forces. This is polar, it undergoes hydrogen bonding forces. If they're not the same, you just decide on the stronger force, which is the hydrogen bonding. Okay, what's the name of these? What's the name of this? Ethanol and butane. Funny story, I tutored somebody else from another school and he said butane. I was like, no, it's butane, but it made me laugh. He was like, but. And I was like, nope, it's but.
Wait, like an AP kid?
No, it's an honors kid. Poor little guy. Okay. So we have an alcohol versus a straight chain alkane. What do you guys think?
Alcohol.
Why?
Because it can combine hydrogen.
Right. So I want you to note, and this is something that's kind of new. We actually can consider both halves of the molecule. This half over here can undergo hydrogen bonding. This half over here can undergo LDF, London dispersion forces, because it has mainly nonpolar bonds on that side, or nonpolar component. This one is just a big old carbon chain, so it's only going to undergo London dispersion forces. So because the combined or the summative intermolecular forces that this one can undergo is stronger than just the London dispersion force, we're going to choose the alcohol. But sometimes later on in life, if we have, let's say, octane with 8 carbons and lots and lots of surface-to-surface contact and lots of London dispersion forces, sometimes a summative London dispersion force across a very large chain can outdo or be stronger than something with hydrogen bonding. Okay, so note that there are exceptions to those. Hydrogen bonding is the best kind of rule. We will learn sometimes that like octane or something might have a stronger force of attraction than something else with an alcohol group. It just depends. So we'll look at physical properties to help us see that though. Next thing, what kind of thing is this? That's an ether, because there's something on either side of the O. What kind of ether? I'll give you a start. Diethyl ether. Good. This is diethyl ether. This is pentane. So who's the stronger? Diethyl ether, because it is polar, right? You got a big oxygen, 2 lone pairs, so it looks like this. So I'll draw that again on near Easter. Looks like an ether bunny. Ether. Okay. So this is polar. It undergoes dipole-dipole forces, not hydrogen bonding. This is London dispersion forces only. This is London dispersions as well, because we got 2 ether groups or ethyl groups on either side. So this would be dipole-dipole plus London dispersion, which is stronger. So that would be summatively stronger. So that would be the higher force here. All right, let's knock out the other one. If I can finish it. Both of these done, guys. Am I going too fast? You guys okay? Okay, we're talking through this. So highest freezing point. what I say was the same thing as freezing point. Melting point, because most people are like, freezing point, it's hard to conceptualize that, but freezing point's the same as the melting point. It's just opposite in phase change, right? So if you want to think of it as melting point, that's cool. What type of molecule up here? What can you narrow it down to that can have the highest freezing point?
Ionics.
One of those ionics. Because ionics, do you ever see them in liquid or gaseous phase?
No.
No, we generally see them in solids. So their melting point, aka freezing point, are really high. Which one's the strongest one? Because, right, you need to be able to verify or confirm or support your decision. Charge product of 2 plus times 2 minus is stronger than the charge product of -1 and then a +1. These other ones are covalent, 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 so polar and nonpolar, whatever, ionics is stronger. Highest heat of vaporization. What does heat of vaporization refer to?
Boiling point.
Okay, basically, so specific and less specific, but basically we're going from phase changing from what to what? Liquid to gas, 1 mole of it, the heat required. Endothermic, great. Okay, what's the relationship? The higher boiling points and heat of vaporizations and all that jazz goes with what? Higher IMFs. There's only one that is opposite. I said this in the video. What kind of pressure? Vapor pressure. So which ones have higher vapor pressure? Ones with lower IMFs, because they're just like, all right guys, bye, and then they overcome their IMFs, and then they start bouncing around the container causing vapor pressure. That's the only one that's counterintuitive. Yeah.
So why is people like use mercury for
Thermometers.
barometers?
Well, mercury itself is going to be metallic bonding with
So it
itself.
doesn't have big.
Right, it doesn't have high vapor pressure, so it's the kinetic energy that's being transferred from the thermal source that's creating the temperature to go up. Yeah, because they don't cause vapor pressure themselves. But alcohol thermometers, they're safer, but they're
No,
less
I'm talking
reliable.
about like the pressure tubes.
Yeah, like a barometer.
Yeah, for water you have to calculate vapor pressure with mercury.
Yeah, but it's because of because of their inherent properties. But there's other uses too. You can use them for like based off thermometers as well, because they're not affected by pressure. Yeah. Okay. So back to the question. What do you guys say? I like identify the IMS for each of these. This one. So London dispersion. I'm gonna really write this really tiny so that Lewis can see this. Okay. London dispersion force. Okay. This one. London dispersion force and silicon.
Yeah, it's to be ion.
It could be, but did you guys see network covalent solid? Okay. If silicon is involved, and you'll watch another video Monday. That includes network covalent. This one's a network covalent solid, and so basically that is similar to quartz.
Yeah, that's what
Okay, similar quartz. Silicon dioxide is quartz, which is like a solid, but it's not an ionic solid. It's a molecular solid called a network covalent solid because it's nonmetal. Silicon is a metalloid. It actually generally acts as a nonmetal. Okay, silicon is used in lots of different things. So the answer would be the network covalent solid is a very high melting point. We'll get into that more, but this is that kind of your preview. Lowest boiling point. What is that really looking for there? So the weakest IMFs. Who has the weakest IMFs up here? Butane, not.
ethanol.
What is it? 3 carbons. Propanol. So not propanol because it's got a hydrogen bonding component. This one is butane, but that's going to have London dispersion only. Okay, you're writing down these little extra notes that I'm saying out loud, okay? Lowest vapor pressure, what's it actually looking for? Why highest IMF? Because it doesn't vaporize easily. Okay, so who's going to have the highest attractions? Which one's hydrogen bonding? Okay, so this one has 2 places for hydrogen bonding. It's the H to H and the double lone pairs on there, okay? So I'm going to just denote that as 2 hydrogen bondings. This one only really has 1 location because it's 1 OH bond, versus this one with 2 OH bonds. So this one actually has London dispersion on this side and hydrogen bonding on this side, but this one is better. We all know methane's out as London dispersion. Cool? So water is the best one here. Lowest vapor pressure. Most viscous, what's it asking for? Highest IMS because it's going to be really sticky on each other. Sticky is a relative term. Do not say that on the AP exam. So do not say sticky. So which one's gonna be most sticky? Why?
It has
Two places for hydrogen bonding on the sides. This one's got one place for hydrogen bonding. This one does not hydrogen bond. Okay, so two alcohol groups creates bigger viscosity, more hydrogen bonding. Huh? No, that's a one. Okay, that's 1,2 ethanol because there's two alcohol groups. So you have to name each carbon. That's the track it's on. Next question. What is this? Oh, this is down here. Okay. Lowest enthalpy, what's it asking for? Highest IMF would mean that it takes a lot of energy to melt it. Low IMF, so it means it takes very little energy to melt it. So remember, fusion is melting solid liquid, so which one? So first of all, we already ruled out the ions, right? They're gone. They're super high melting point. They have a high enthalpy of fusion. We have a nonpolar London dispersion. We have another nonpolar London dispersion. What is this? That's polar. Carbon monoxide has a dipole moment pointing towards the oxygen. So compare these. What are you comparing? Electrons. Because electrons. Which one has less electrons? Nitrogen, because less electrons means you have less shifting of electrons. Less shifting of electrons is less polarizable. Less polarizability means lower LDFs. So LDF is lowest on the nitrogen. Greater surface tension, what's it asking for? Highest IMF. Who would have the highest IMF? Propanol. Use your words. This is propanol. Why propanol versus, what's the name of this? This is what's the functional group of C double bond O?
Yes.
What is the functional group? No. Well, okay. Give me. It's an aldehyde or ketone.
Yeah, ketone.
Well, yeah, it does. But tell me where it is. It's in the middle, right? Is it a ketone or aldehyde? Ketone. Keys go in the middle of the lot. Okay. Ketones are in the middle. Aldehydes, I don't know. Aldehydes are on the end. So this is a ketone. This is propanone. Pro 3. Okay. Anyway, hydrogen bonding, not hydrogen bonding. What is this one undergoing? There's a dipole moment here. Shh, come back with me. I got a couple more minutes. This is dipole because we got a C to O group, which is the dipole moment, not hydrogen bonding. This one's hydrogen bonding, so this one would be the stronger one. Last one, highest boiling point. What are we looking at? Yeah. Okay, so since they all have one what? So one hydroxyl group, which would undergo one hydrogen bond each, with everything else being equal, what do we compare? Molar mass. So this one being is 1, 2, 3, 4. 1, 2, 3, 4. Butanol, propanol, and ethanol. Butanol wins because, and this is going back to that summative part again. We have hydrogen bonding plus lots of LDFs because we have this big, huge carbon chain. Medium LDFs, small LDFs. So the summative nature of the lots of LDF and the hydrogen bond makes it the strongest type of molecule attraction. So are you guys comfortable with like explaining the summative nature of these? Because we didn't do that in honors chem at all. Okay. Okay. So you guys can do the last bit. Identify the crystal. I'll give you lesson 5. Figure it out. Because some of you guys are not even paying attention to me, which is kind of rude. I'm trying to help you out. So you have to do this at home. I want to go over these before you go, due to lack of time, let's do this together. Melts below 100 insoluble in water. What kind of compound? Right, nonpolar molecular is how I want to say that because it's a molecular solid. Your options are ionic, metallic, molecular molecular polar or molecular nonpolar and network. Okay, so there are like 5 options here. So the first one definitely is, why is it nonpolar? Right, nonpolar molecular. I'm going to go like that, okay? Conducts electricity only when melted. Ionic, because that's the only, other ones would conduct electricity. And I do want you to denote to yourself someplace on this paper, dissolves does not mean ionize. Those are 2 different terms. Dissolve just means get surrounded by water. Ionize means make ions. 2 different things. Okay, keep going. Insoluble in water conducts electricity. Metallic, because anything that's not going to dissolve is not going to be ionic, possibly not molecular, but the fact that it's conducting electricity, not dissolving, would be metallic. Insoluble in water melt above 500 does not conduct electricity with an asterisk because it does. There's one example. Yes, what is the network? So most network covalents do not conduct electricity. Okay, most of them don't. There is one. Graphite. And graphite, you'll see a big blurb on that on Monday. So that's a network covalent. Those are giant molecules, giant crystals. There's lots of words for that. Dissolves in water, not conducting, either aqueous, solid, or molten. Why polar? Polar. Like dissolves, like non-polar. Okay, so polar molecule, and then why is it molecular though? What characteristics say that? So we know that dissolves in water is the polar part. Non-conductive. In any form, shape, or way. Okay. So that's why it has to be molecule. Dissolves in water, melts above 100, conducts electricity when present in aqueous solution. Ionic. And so there are 2 ionics here because I just want you to note that molten, meaning molten ionics conduct electricity, and when they're dissolved in aqueous solution, conduct electricity. But in their solid state, do they conduct electricity? Absolutely. Great. Okay. So you guys have 2 FRQs to do for homework, and this one right here. You see that? It was just IPF examples. There's 11 of them. It's basically what we're just doing. I just want to make sure you're good. And then Monday, I'll upload the lesson plans and everything online for you guys for Monday. I'll take pictures and send them to you from California.
Are you going to have the stuff collected on the stairs?
I'll get stuff on Wednesday. Oh, grab your lab notebooks. Wednesday we're doing a lab. Okay, so grab your lab notebooks and I'll upload everything for you. The FRQs we'll kind of slowly make progress on.
Wait, so why are you going to California?
UNC Charlotte sending me to present for 20 minutes.
For 20 minutes. They're paying for you.
What are you presenting?
San Diego, presenting about a semiconductor polymer kit I created this summer with the help of actually Jack and Nikhil. But we made a program out of it and training teachers on it. Did I ever start recording? Yes. And